Hello dear students, hope you are in good health and spirits. And myself, Dr. Amrit Pal Singh, and I welcome all of you again on this online learning platform. In our today's lecture, we will discuss about the representation of nuclear forces. In this, we will discuss what type of exchange forces which exist, and due to these exchange forces, how the interaction between these neutron and proton it is being happening within the nuclei, and then we will discuss about the various types of nuclear potentials which has been explained by the Wigner, and using these nuclear potential we can calculate we can solve the Schrodinger wave equation in order to study the differential cross section or the total areal cross section for a particular NP scattering experiment or for a PP scattering experiment. So in the meantime, so you just write your comment in the comment section so that I can get to know that how many people are online, so that I can start. So majority of the people, there are 13 people which are connected. So let us start our today's lecture. So first we will discuss the types of nuclear potentials. Now we all know that the nucleus it is a complex structure, and for a higher atomic number nuclei, and here there are a large number of nucleons which are present. So but in the simplest form, like if we are considering a neutron problem in which there is only one neutron or one proton, then we will solve these nuclear interaction, and we consider it to be a central interaction, and these type of interaction they are generally assumed to be attractive. But when we are talking about the many body problem, then we have to drive the Schrodinger wave equation for each interaction. Then there is the non-central character of nuclear forces which comes into line, and then we our analysis it becomes complex. So starting with the simplest form of interaction, that is with the neutron problem. So Wigner has proposed a model. So he represented a nuclear form, so in the form of a square well potential. So I will draw here. So this is something like the range. So if this side you can say that this is range or the internucleon force, and this side this is our nuclear potential. And upper side it is representing the repulsive nuclear potential, and lower it is representing the attractive nuclear potential. So as I have explained in my previous lectures, so it is something like this structure, and this is for the ground state of a neutron problem. So this is for the ground state of two body problem, and when we are talking about the excited state, then the value of this nuclear potential it changes, and that we will also drive that how these values it is different for different excited states. And this is the minimum value of the impact parameter, which you all known as the value of B, and which is of the order of 0.5 femtometer. And when the difference between the nucleons it exceeds the value of 0.5 meters, so here you can see that, so this is some sort of a well, and in this well there are attractive forces. So as this is the final boundary of our square well, and when the potential it exceeds this square well potential, and you can see that, so here there is the separation of nucleons which take place. And the value of this R naught, that is different for different nuclei, and it is approximately from 2 to 4.2 femtometer, and for a deuteron its value is approximately 2 femtometer. So Wigner represented the simplest form to solve this nuclear potential, so using the square well potential problem. So what he has said that, so Vr is the nuclear potential that is at a particular point, and minus V naught, which is the nuclear potential. So when the particle it is they are bound or they are within the potential well, and we can derive something like with the ratio of R over R naught. So R naught is the maximum distance with which that particle can move within the square potential, and R is the particular position of that particle and its value changes. So this is for R greater than B and up to R is equal to R naught, and the value of Vr that approaches infinity. So when the particle it comes out of the box, so when the value of this B that exceeds the value of R naught or R, so in that case, so we can derive the value of this V naught, that is for different states with which these two particles they are bound. And generally for the deuteron problems, so they have found that the value of R naught that is of the order of 2 femtometer, and the nuclear potential for the ground state of deuteron, so that is generally of the order of minus 30 mega electron volt. So what does it means? That is the bonding energy of the nucleons in order to have a bound system, so it should have a value of 30 mega electron volt, and this we will derive in our next lecture when we will derive the deuteron problem using the Schrodinger wave equation. And before that I want to explain about what type of various these potential model which we can explain these nuclear potential. So first type of model which Wigner has explained, that is the square well model. Square well, or you can say rectangular nuclear potential, and you all have studied this model using the particle in a box using the potential square well potential. So during your graduation classes, what we have done is we have considered the value of nuclear potential, so when it is within the box, and the value of this nuclear potential, so when there is no bound system between the nucleons, and its value goes to 0. So where R is the relative coordinate. So the last equation which I have explained, that is the general form of nuclear potential, and which we can represent for various nuclear potential, but for this square well potential, so this is the standard model, so which he has solved. So R is the relative coordinate of two nucleons, and V naught is the depth of the potential, and the parameter R naught that represents the range of the nucleons. So when the value of this R it is less than R naught, in that case the two nucleons, so they are bound and having this much nuclear potential, or they are present within the square well. And when the value of this R, that is the coordinates between two nucleons, its value exceeds the range of two nucleons, and these two nucleons, so there is a breakage of bond and they no longer remain a bound system. So at that point we have considered that the potential is 0. So second potential, using the exponential potential, we can also solve this nuclear potential for the two body system. Exponential, so spelling is exponential potential, and its representation is something like, so they meet at a point, so that is representing the bound system. So this is the value of exponential potential. So at this point, so it is having a maximum value, and when the value exceeds, so at this point, so its value is V naught over E, and that we will also discuss using the single point model or the Yukawa potential, and we will drive this relation. So for a single point model, so the maximum value it can have, that is of the order of minus V naught over E. So this is the representation of exponential potential, and the nuclear potential which we can calculate using the exponential function e raised to power minus r over r naught, or at a maximum value when r is r naught, so at that point the nuclear potential, that is of the order of minus r naught over r naught, so that is minus v raised to power e inverse, that is minus v over e. So this is the exponential. Using the exponential function we can also drive the interaction between the nuclear potential, and using the various NP scattering interaction we will use this function in order to find the total area cross section, or the differential cross section, or the scattering amplitude of a nucleus. So third form, that is the Gaussian potential. So Gaussian function, using we can solve this nuclear potential equation, that is minus r square over r naught square, and again using this Gaussian function you can see that, so when the value of r is of the order of r naught, and at that point the value of this nuclear potential, so it is the same which we have derived for the exponential potential or for the square well potential problem. So all type of potential, they are giving the same sort of potential, nuclear potential value. And the next type of nuclear potential which we can use in order to solve these NP scattering interaction, so that is the Yukawa potential. So the Yukawa representation is more or less something like the exponential function. So this is our value of V. So at this point it is V naught, and so at this stage this is minus V naught over V naught, and this we will drive in detail when we will discuss the single point model. So the Yukawa potential, it has been explained by this Japanese physicist, that is its value is minus V naught e raised to power minus R over R naught over R naught of R over R naught. So this is the Yukawa representation. So using this nuclear potential form, he have derived the nuclear potential for different nuclei. So again you can see that when R is of the order of R naught, so at that point of the value of this nuclear potential, that is of the order of same nuclear potential. So similarly there are some other forms of nuclear potential. So with using that you can solve your two body problem or the multi body problem. So the last type of potential, so that is the Woods section potential, and whose representation is something like, so this is the value of minus V naught. So at this point, so its value is minus V naught over 2. So this is the representation of Woods section potential. So where he has considered the function of phase shift. So that is how the change in wave amplitude of a neutron and proton, and there is change in potential value for these cases. So here sigma is representing as the shift parameter. So VR is, we can also write it R minus R naught over sigma inverse. So this is the representation of Woods section potential, and generally, so from competition point of view, and sometimes they can ask you the representation of any type of nuclear potential, or they can provide you the figure of a particular nuclear potential, then you have to identify so what type of nuclear potential that is. So next we will discuss, so apart from these type of wooden section potential, there are some other forms which have been explained by the Friesberg, and some other forms that has been used by the Bartlett. So but I will not go in detail in that forms of nuclear potential. And so next we will discuss the exchange of nuclear forces, exchange character of nuclear forces. So far, we have discussed mainly the character of forces which is acting between pair of nucleons, and when we come to consider the system comprising more than two particles, so we must accept to have some sort of complications, so which enter even in our nuclear potential system. So using the multidimensional problem, we have to deal with some certain quantitative aspects of nuclear forces. So these quantitative aspects which becomes important when we are not taking two body problem, but for a multi-dimensional problem, so these some sort of quantitative aspects which we have to consider. Now what are these two aspects which we will generally consider for this neutron problem? So that is the saturation of density, saturation of nuclear density. So what does it mean? The density of nucleons is roughly equal to all the nuclei. So whether we are talking about a two-body problem or we are talking about a multi-dimensional problem, so ਉਸ ਕੇਸ ਦੇ ਵਿੱਚ ਕੀ ਆ ਕਿ ਜਿਹੜੇ ਨਿਊਕਲੀਓਨਸ ਡਿਊਟਰੋਨ ਦੇ ਵਿੱਚ ਪ੍ਰੈਜ਼ੈਂਟ ਹੈਗੇ ਆ, we have considered that, or the nucleons which are present in a high atomic number nuclei, so their density, so that is almost same, so that is the saturation of density occurs. So second, we have considered the saturation of binding energy. So it means that the binding energy for all the nucleons, it is roughly equal for all the nuclei. So binding energy per nucleon is roughly equal for all the nuclei. So although these assumptions, they are not correct, they have been proved that these assumptions are not correct. So when they have solved the Schrodinger wave equation for a multidimensional nucleon problem, so but at the early stages they have been considered these type of postulates in order to drive a model. So these are some of the assumptions which have been startedly considered by some experimentalists, something like the Wigner or the Majorana. So they have considered these assumptions. Now, what are exchange forces? So exchange forces, we will investigate four type of exchange forces which exist within the nucleons. So it has been mentioned in my previous lecture that the nuclear forces, they are not only the position dependent, but they are also the spin dependent, and their dependence, it is changing with respect to position coordinate and with respect to spin orientation. So this we will also prove in our nuclear scattering experiment, that the nuclear forces are of exchange character. So what type of exchange character so they can exist? So there can be space exchange character, or there can be spin exchange character. So space change means, so when one neutron, it is being interacted with the other neutron or with other proton, so that neutron, it exchanges the space, or it exchanges the position with that other nucleon with which it is being interacting. So similarly, when it exchanging its speed, it is transferring its momentum to that particular neutron, and there have been laterally added by the Bartlett and Friesberg. So there is not only the space exchange character which is present within the nucleon, but apart from that there is spin exchange character that can also be present. So for example, this is a proton which is having a upper spin of half integral spin, and when it is interacting with the other neutron, and it can transfer its spin, so this neutron, it can again have this up spin character or down spin character. So depending upon how the orientation or how the interaction it has been taken place between these two particles. So later the Hassenberg modified that a particle at a time not only can exchange or not only can exchange a spin, but it can exchange space plus spin both at the same time. So first type of forces, so which we will discuss. So how we represent these forces? So we represent these forces or the wave equation using the Schrodinger wave equation. So let us say this is our wave equation, and this is our Schrodinger wave equation. So where the wave function, it is representing the position coordinate of two nucleons, and it is representing the spin coordinate. So the position coordinates, it is generally represented with the term r. So this is representing position coordinate, and here this polyspin operator, so which is representing the spin character or the spin coordination. Or we can also write it as something like psi 1 2 or psi 1 2. So this 1 2, that is quite prominent, and it is can be changed when these two nucleons, so they are interacting. So this one, that is representing the position of first nucleon, this is representing the position of second nucleon, and similarly this first, it is representing the spin of first nucleon, and this is representing the spin of second nucleon. So first type of operator or first type of forces which exist between these two nucleons, so that is generally known as the Wigner force, or we also call it as the ordinary force. So what Wigner, it has represented that the nuclear potential, it is dependent upon a operator that is known as the Weigner operator, and this operator, it has a constant value that is equal to 1 for all the states, and using this Wigner force, so he has represented the Wigner potential which we have derived or which we have discussed in the previous slides, what type of various Wigner nuclear potentials, so which we can use in order to find the NP scattering interaction. So this would make the equation h square over m del square psi, or we can keep the psi outside, psi 1 to theta 1 2. So that is equal to Vr P omega psi 1 to psi 1 2. Now this Wigner operator, it do not change either the position coordinate of the nucleons, or neither it change the spin coordinate of the nucleus. So the interaction potential has the same sign in all the states. So since it is attractive, we will drive, so what is the interaction, or what is the potential for the nucleons which are present in the s orbital, what is the interaction which the nucleons which are present in the excited state like in the l orbital or in the p orbitals. So for the ground state nucleons which are present in the s state, so where the value of l, that is the angular momentum, is 0, so the value, it is attractive for all the states. And what he has said that, so far the nucleons which are present in the s shell, so its value is attractive, and this does not produce any saturation. But the idea of this Wigner operator, it has been proved wrong, because what Wigner has considered, Wigner has gave his theory based on two assumptions. So Wigners ने किहड़ियां assumption consider कीतियां सी. So first assumption Wigner has considered is the nuclear force acts between the pair of nucleons and is not influenced by the presence of neighboring nucleons. विगनर की कहता कि जिन्ने भी ਜਿਹੜੇ ਨਿਊਕਲੀਓਨਸ ਕਿਸੇ ਵੀ ਜਿਹੜੇ ਨਿਊਕਲੀਅਸ ਦੇ ਵਿੱਚ ਪ੍ਰੈਜ਼ੈਂਟ ਹੈ ਸੋ ਉਹਨਾਂ ਦੀ ਜਿਹੜੀ ਇੰਟਰੈਕਸ਼ਨ ਹੈਗੀ ਆ ਇਟ ਐਗਜ਼ਿਸਟ ਇਨ ਦੀ ਫਾਰਮ ਆਫ ਪੇਅਰ and the other nucleons so which are present, so suppose this is our nucleus and there are number of nucleons which are present, and the interaction of the nucleons it is in the form of pair, and these pair it do not have any interaction with the pair which is present in its neighbor. So second assumption he has considered is the nuclear force between the nucleons is velocity independent. And is always attractive. So as he has explained in his Weigner operator that the nucleons which are present in the ground state of neutron, that is for the triplet state of s orbital, so there are only attractive forces which exist between the nucleons, and it is independent of type of the nucleons. And is the same for all relative orbital angular momentum. So what does it means? So it is attractive for all the values of L. So we all know that when L is equal to 0, then the nucleon, or if we are talking about the nuclear structure, so the nucleon which is present in the s orbital when L is 1, so nucleon is present in the p orbital, and similarly for 2 it is present in the d orbital when L is 3. So it is present in the f orbital. So this all we will derive in using the shell model. So how these nucleons, so they are present in the form of shells. So for all the values of the orbital angular momentum, so all the forces which exist between the nucleons, so that is attractive. And third consideration he has considered that the nuclear force, it is predominantly a central force. So using these three assumptions, he has given this Wigner force, and he has explained this Schrodinger wave model, and he has derived the value of this Wigner operator, and which is independent of the value of position coordinate, or it is independent of the value of space coordinate. But these assumptions, it has been challenged by some other scientists like Majorana and Bartlett, and later on, so their theories, it has been challenged by Hassenberg, so who also gave the concept of isospin that we will discuss in our later lectures. Now what they has challenged, so Majorana, so first before explaining the Majorana potential, So I would like to explain how these assumptions of the Wigner it has been make correct. So because they do not follow the real model. So first assumption of Wigner, that is incorrect, because we all know that the force between two nucleons is attractive for distance r greater than d and is repulsive when the value it is less than value of d. So in some books it is mentioned in terms of b, so you can use only one notation. So based on that, when two nucleons, so they are quite close to each other, that is less than the value of 0.5 femtometer, in that case there is some sort of repulsive forces which is stopping these two nucleons from collisions. So when these two nucleons, so they are going apart, then there is some sort of attractive forces which comes into line, and so that is at a distance up to value of 4.2 femtometer. So these assumption that is our real assumption, and they make the Wigner assumption wrong. So second assumption, the force between two nucleons is attractive and repulsive. There are both type of forces which exist within the nucleon, while Wigner has considered that there is only attractive forces which are present between the nucleons. So again, this is wrong. So what is the Majorana Space Exchange Force? So second type of exchange force, so that is known as Mesorana Space Exchange Force. So Majorana said that the nucleons, so when they are interacting with each other, so they can exchange their space with respect to each other, and he represented the nuclear potential. How we can represent the nuclear potential? So that is with the operator which is known as the Majorana operator, or we also call it as the space exchange operator. So this PM is Majorana operator, we also call it as space exchange operator. So what he said that, so when we apply the operator to a wave function of a wave, so this is the total wave function, this we can write. So this is the position of first coordinate, this is the position of second coordinate. So after the operation, so there is exchange in position between these two nucleons. So you can see that, so this nucleon position it has been changed to this, and this position it has been changed to first point. So we can write it as psi 1 2. So this is how these two nucleons, so they exchange their position, so when they are interacting with this each other. So the operator PM has the effect of interchanging the space coordinates of two particles. Now the effect of this operator is equivalent to that of the parity operator, and he represented this operator as the parity operator. So what is our parity operator? So he said that it is dependent upon the orbital angular momentum of a nucleon, and with the change in value of the orbital angular momentum, so the value of this Majorana operator it is being changed. So where L is the orbital angular momentum. And from that you can write the Schrodinger wave equation for this Majorana operator. Psi12, that is the position coordinate, so this is our space coordinate, and this is our nuclear potential, this is our operator, this we can write. So when this Majorana operator, it is being interacting with the position coordinate, so it's changing its position, so we can write this term as Psi12, and this is eta12. Or you can also write this term as minus 1 the power L VR Psi12 Psi12. So putting the value of Pm in this operator, so we get this equation. So it is different for different value of L. So that is, there is attractive forces. So when value of L is 0, or when value of L it is even, and there is repulsive forces which exist between the nucleons. So these forces are repulsive when the value of L is odd. So NP interaction potential, it is attractive so there is attractive NP potential for s orbital, because we all know the value of L is 0 for s orbital, and it is attractive for all even values or all even L states, and it is repulsive for all odd L states. So odd ਦੇ ਵਿੱਚ ਕਿਹੜੀਆਂ ਆ ਜਾਂਦੀਆਂ? So it is repulsive for p orbital, f orbital, so and so. So there exist both type of attractive and repulsive forces between the NP interaction potential. So this type of forces, that is known as the Mesorana forces, so it provide saturation. So saturation in forces which exist, and that is correct as explained in our NP scattering interaction. So after the Majorana potential, so third type of exchange force which exists, that is known as the Bartlett or spin exchange force. ਹੁਣ ਬਾਰਟਲੈਟ ਨੇ ਕੀ ਕਿਹਾ? ਬਾਰਟਲੈਟ ਕਹਿੰਦਾ ਕਿ ਜਿਹੜੇ ਨਿਊਕਲੀਓਨਸ ਆ ਜਦੋਂ ਇੱਕ ਦੂਸਰੇ ਦੇ ਨਾਲ ਇੰਟਰੈਕਟ ਕਰ ਰਹੇ ਆ, so they can exchange their spin as well, and this we have derived also during the NP scattering interaction experiment at low energy, or the PP scattering interaction at low energy, that how there is a change in spin between the nucleons, and he derived the nuclear potential, so in terms of a operator that is known as the Bartlett operator, or also known as spin operator. And when this operator, it is applied upon this sigma value, so where sigma, that is dependent upon the Pauli spin operator, sigma 1, sigma 2, and there is change in spin between these two nucleons, and this we can write as xi21. So this PB operator, it interchanges the spin of two nucleons. So you can see that, so when we apply this PB operator to this spin wave function xi12, and it has changed its position from xi12 to xi21. So for two particles of half spin, there are three symmetric spin states which exist, that is known as the triplet state or singlet state, that we will discuss in our further lectures. So for two nucleons, so that is having the parallel spin space, so 1 by 2, 1 by 2, so in that case the total spin, it comes out to be plus minus 1. So plus 1 if there is the up spin for both the nucleons, and minus 1 if there is down spin for both the nucleons. And there exist three spin states, and for the anti-parallel spin there is only one antisymmetric state. So when both the spin, they are anti-parallel. So at that cases, the value of the total spin, it get cancelled. So how this value of spin operator, it is changing the spin of these two coordinates. So this we can write minus 1 s plus 1. So he derived this spin operator which is dependent upon the spin of particle as minus 1 s plus 1 sigma 1 sigma 2. So this we can also write it as sigma 1 2. So this is how the Bartlett operator, it is changing the spin of these nucleons. And when we implement this in our Schrödinger wave equation, so our wave equation becomes so this we can write the nuclear potential VR, this is the Bartlett operator. So this is our position dependence, this is our spin dependence. So this becomes minus 1 s plus 1 xi12 sigma 12, and the value is attractive nuclear potential. So when it is attractive, when the value of s is equal to 1. Here s, that is representing the total spin of two nucleons. So for the triplet state, so the nuclear forces, they are attractive, and when there is anti-parallel spin, so at that case the value of this total spin, that is equal to 0, and for all the singlet nuclear state, the nuclear forces, they are repulsive forces. So hence all triplet state forces, so all triplet state forces, so triplet ਦੇ ਵਿੱਚ ਕਿਹੜੀਆਂ ਆਉਂਦੀਆਂ, so that is S state triplet, P state triplet, D state triplet, so and so. So these all triplet states of all the nuclear orbital or all the shell orbitals, so they are attractive, while all the singlet states, So singlet state, that is the singlet state of s orbital, singlet state of p orbital, singlet state of d orbital. So these all are repulsive, and this is according to the Bartlett Spin Exchange Operator. While so the expression of this Bartlett, it has been proved wrong, because experimentally when we do the NP scattering experiment at low energies, that is of the order of 10 MeV of proton or neutron energy, so it shows that, so the results of this experiment, it shows that the value of this singlet s orbital nuclear state, it is attractive in nature. So which contradicts the above theory of this Bartlett operator, and according to, you check here, according to this Bartlett operator, the value of 1s, it is repulsive, while according to this NP scattering experiment, the value of this 1s orbital, that is attractive in nature. So the experimentally its values, they are not correct, and it has been contradictory values. So further it has been considered that the Bartlett spin exchange force cannot be the only type of exchange force which is present between the NP system, and there is some sort of other nuclear force or other type of interaction which is happening between these neutron and protons, so when they are interacting with each other. And later on there is fourth type of forces which has been explained, and that is known as Hassenberg Force, or we also call it as space plus spin exchange force. So what Heisenberg has said, that the nucleons like the proton or neutrons, so when they are interacting with each other, and there can be exchange of spin and there can be exchange of space at the same time when they are interacting with each other, and he derived the nuclear potential, so in terms of operator which is known as the Heisenberg operator, or we also call it as space plus spin exchange operator. So applying this operator, it interchange both the spin and space coordinate of the nucleons. So when we apply this operator to our total wave function, so it exchange the value of position as well as the spin of this operator. So what are our final position, that is being changed, so spin is also being changed, and we can write it as xi21 sigma 21. And further he has represented that since it is dependent upon the space and spin of the nucleons, so its total value, it is sum of the orbital angular momentum plus the spin angular momentum. So he represented this operator P as minus 1 L plus S plus 1. So this is the form of Heisenberg operator. So when we apply this operator to our Schrodinger wave equation, so from that we can find what forces are attractive and what forces are repulsive. So this is our nuclear potential VR. So when we apply this operator, so this becomes minus 1 L plus S plus 1, and it changes the value of this nuclear potential. So these forces are attractive. So when these forces are attractive, when L is 0 or even and spin is parallel spin, or again this force is attractive when the value of L is odd and S is 0. So in these two cases, the nuclear forces, they can be attractive in nature, and similarly these nuclear forces, they are repulsive, and they are repulsive when L is 0 and S is 0, and again they are repulsive when L is odd and S is 1. So there are two cases for attractive forces and there are two cases for repulsive forces. So what Heisenberg said, that the force is attractive in triplet state of s orbital, triplet state of d orbital, and also it is attractive for singlet state of p orbital, it is attractive for singlet state of f orbital, and forces are repulsive so it is for 1s orbital, singlet state of d orbital, and triplet state of p orbital and triplet state of f orbitals. So again you can check that the NP scattering experiment, so it is showing that the 1s force, it is attractive in nature, while according to this Hassenberg force it is showing that it is repulsive in nature. So again there is a contradiction between the value of the theoretical results and the experimental results. So again they have said that these are not only the four type of forces which exist between these nucleons, so when they are interacting with each other, and there is some sort of other interaction so which is present between the nuclei or nucleons, and later on Heisenberg modified its theory and he represented one another form which is also being exchanged when these nucleons, so they are interacting with each other, and he gave the concept of isospin. So total there are three type of exchanges which is being happened. So one, it is the position coordinate which is changing the value of the two positions of the nucleon. Second, it is the spin coordinate, and third, it is the isospin coordinates. So this represent how the isospin of the nucleons, so it is being exchanged so when they are interacting with these nuclei, and this we will discuss in our coming lectures. So I hope you have understand this today's lecture. So if you have any queries, you can write in the comment box. So also in the meantime, you can like or you can comment in between the video if you feel something like that, or if you have any type of question, you can ask me by typing your queries in the comment box. So I will try to explain and at the later stages if you have any type of problem related with this topic. So again we will meet you again on this platform, so with the new topic of nuclear physics. So till then, goodbye, see you in the next lecture.